The Big Bang Theory is our best explanation for how the universe began. It's a fascinating story that takes us back billions of years to the very beginning of everything. Imagine a time when there were no stars, no planets, not even space itself. What existed then? That's the question the Big Bang attempts to answer. According to this theory, the universe began from a state of incredible density and temperature. It wasn't an explosion in the traditional sense, but a rapid expansion. Everything we see around us today, galaxies, stars, planets, even ourselves, originated from this initial event. The Big Bang is a story of cosmic evolution, a journey from a tiny dense speck to the vast universe we observe today. One common misconception about the Big Bang is that it was an explosion. This isn't accurate. Instead of an explosion happening in a pre-existing space, the Big Bang was the expansion of space itself. Picture a balloon with dots drawn on it. As you inflate the balloon, the dots move farther apart. Similarly, as space expands, the objects within it, like galaxies, move away from each other. The Big Bang happened everywhere at once. There wasn't a single point from which everything exploded outward. Instead, space itself began expanding and continues to do so today. This expansion is a fundamental aspect of the Big Bang theory and has been confirmed through numerous observations. The Big Bang theory describes the universe starting from an extremely hot, dense state about 13.8 billion years ago. It's hard to fathom, but everything we observe in the vast cosmos was once concentrated in a region smaller than an atom. This incredibly dense and hot state is often referred to as a singularity. In the first fraction of a second after the Big Bang, the universe underwent a period of rapid expansion called inflation. During this inflationary period, the universe grew exponentially in size. Imagine a grain of sand suddenly expanding to encompass the entire observable universe. That's the scale of inflation. This rapid expansion helps explain the uniformity we observe in the universe today. Immediately after the Big Bang, the universe was incredibly hot and dense. It was so hot, in fact, that matter as we know it couldn't exist. Instead, the universe was filled with a sea of elementary particles like quarks, leptons, and their antiparticles. These particles interacted with each other at incredible speeds. As the universe expanded, it cooled. This cooling allowed for the formation of more complex particles. For example, quarks combined to form protons and neutrons, the building blocks of atomic nuclei. This era, lasting from about 10 to the minus 6 seconds to 1 second after the Big Bang, is known as the quark epoch. During this time, the universe transitioned from a sea of elementary particles into a soup of protons, neutrons, and other particles. Section 5. The building blocks of matter, quarks, and more. As the universe continued to cool after the quark epoch, a process called nucleosynthesis occurred. During this period, protons and neutrons began to combine to form the nuclei of light elements, primarily hydrogen and helium. These elements are the most abundant in the universe, a testament to their early formation. Nucleosynthesis is a crucial process in the Big Bang model because it explains the observed abundance of light elements in the universe. The ratio of hydrogen to helium predicted by the Big Bang theory closely matches the ratios observed in distant galaxies and other astronomical objects. This agreement between theory and observation provides strong support for the Big Bang. Section 6. Letting there be light. The first atoms emerge. For about 380,000 years after the Big Bang, the universe remained a hot, opaque plasma. Light couldn't travel freely because it was constantly interacting with the charged particles in the plasma. However, as the universe expanded and cooled, a significant event occurred: recombination. Recombination refers to the era when electrons combined with protons and helium nuclei to form neutral atoms. This transition from a plasma to a neutral gas allowed light to travel freely for the first time. This first light is what we observe today as the cosmic microwave background radiation. Section 7. Echoes of the Big Bang, the cosmic microwave background. The cosmic microwave background, or CMB, is a faint afterglow of the Big Bang, a snapshot of the universe as it existed just 380,000 years after the Big Bang. It's a faint glow of microwave radiation that permeates all of space. The CMB's discovery in 1964 was a landmark event in cosmology. The CMB provides crucial evidence for the Big Bang theory. Its existence and properties such as its temperature and uniformity are precisely what the Big Bang model predicts. Furthermore, tiny temperature fluctuations in the CMB provide insights into the seeds of structure that would eventually lead to the formation of galaxies and galaxy clusters. Section 8. From gas clouds to galaxies, gravity takes hold. After recombination, the universe entered a period known as the Dark Ages. This era lasted for hundreds of millions of years and was characterized by the absence of stars and galaxies. However, gravity was at work during this time, slowly pulling together the clouds of hydrogen and helium gas that filled the universe. Over time, these gas clouds became denser and denser under the influence of gravity. Eventually, the cores of these clouds became so hot and dense that nuclear fusion ignited, marking the birth of the first stars. These early stars were massive and short-lived, but they played a crucial role in enriching the universe with heavier elements. Section 9. The universe's expansion, a never-ending journey. One of the most remarkable discoveries of the 20th century was that the universe is expanding. This expansion isn't just the galaxies moving apart within a pre-existing space, it's the very fabric of space itself stretching. This expansion has been ongoing since the Big Bang and continues to this day. We know the universe is expanding because of something called redshift. Just like the sound of a siren gets lower as it moves away from us, the light from distant galaxies gets stretched, shifting towards the red end of the spectrum. The farther away a galaxy is, the more red-shifted its light is, indicating it's moving away from us faster. This observation provides strong evidence for an expanding universe. Section 10. Evidence for the Big Bang, a compelling case. The Big Bang theory isn't just a compelling story, it's supported by a wealth of observational evidence. We've already discussed the cosmic microwave background radiation and the redshift of distant galaxies. In addition to these, the observed abundance of light elements like hydrogen and helium closely matches the predictions of Big Bang nucleosynthesis. The Big Bang model elegantly explains these observations and many others. It's the most comprehensive and well-supported theory we have for explaining the origin and evolution of the universe. While there are still unanswered questions, the Big Bang theory provides a solid framework for understanding the cosmos. Section 11. Unraveling the mysteries, dark matter and dark energy. While the Big Bang theory has been incredibly successful in explaining a wide range of observations, there are still mysteries to be solved. Two of the biggest mysteries in modern cosmology are dark matter and dark energy. These mysterious entities make up the vast majority of the universe's mass and energy, yet we know very little about them. Dark matter doesn't interact with light, hence its name, but its gravitational influence can be observed in the rotation of galaxies and the motion of galaxy clusters. Dark energy, on the other hand, is thought to be responsible for the accelerating expansion of the universe. Understanding the nature of dark matter and dark energy is one of the most significant challenges in modern cosmology.